Yeah. Hi, everybody. So we are Ivan and Minh. We work in the Git team at Google. So a lot of people ask me, like, what is the interest of Google on Git? And actually, we have quite a lot of things to do in our team, because we're the team that hosts the Android repository. Android is probably the biggest open source project out there, with a lot of active development, so a huge volume of commits coming and going. It's also a repository that contains large binary assets, which is always a pain point in Git. We also host Chromium. If Android is the biggest repository out there, Chromium is also on the top on size of projects, with the extra twist that it runs as a single monorepo. Then we are also the service that hosts the code of other Alphabet companies, like Nest and Verily. And finally, we also run the software that powers the cloud source repository, one of our offerings in the Google Cloud, where, well, it's our hosting service where users can create repositories. So this puts us in the order of millions in repositories in total. So, and what's the problem with this? That we are seeing repositories with the order of 10 million objects. And what's the problem with that? Where usually, when you run a Git clone on your repository, you usually get stuck in that fourth line, the one that says that you are downloading the content. You are there wishing that your internet would be faster. And you barely notice that there is this second line that says counting objects. That usually is very fast in most of the repositories, but when you start to get in the order of millions of objects, the server needs to count how many they are going to send you. And that can take some time. Sometime in the order that we can see clones that takes like 5 minutes before the server starts sending anything back to the client. So another problem that we see in our repositories is that some of them has just huge reference counts, in the order of more than 1 million references. Not only because the developers are happy creating tags and releasing versions, but also because you have builders creating tags for multiple purposes, analyzers. Then if you run your code review systems, some like Gerrit are based on branches and creating even more references. And this is a problem that is well explained in this paragraph from the Git protocol spec. And it says that when you run a fetch, when the client initially connects, the server will immediately respond with a listing of each reference it has. This works well when you have a few, when you have a lot, but when you have in the order of the million, this doesn't scale. We start sending to the client megabytes of information that probably the client doesn't even care about. The poor guy just wanted master. So, and also on the server side, depends how do you structure your backend and how do you store your information. Well, retrieving all those references is not a trivial task. And then another of the problems that you get with the scale is that not everybody uses Git as the standard repository of your source code. You build your commits, you keep your development history, and you share your changes. So some people come to Git with inherited workflows, maybe porting from a different version control system. Then they try to emulate some of those features or workflows, and sometimes not everything fits perfectly with Git. There are cases that Git is used as a DB, not just as a repository. For example, Gerrit that uses it as a DB for the comments, no DB. And yeah, there are other cases where a developer wants to set up a kernel repository that then it will fetch branches from many other repositories. So those are all use cases that you need to support. So in the case that when you start to have many branches, suddenly the negotiation with all of them to know what you need to bring can take up to 30 minutes. So, and to show that these are not abstract problems, these are some stats that we got from our database this week. Before I started working in this team, for me, the kernel, the Linux kernel, was the example of a big repository. Well, the 5,000 references of the kernel are not that much if you compare with the 2 million that we just saw in Android. Yeah, think on those 2 million tags and branches if you need, or references if you need to send them back every time you try to do a fetch. And then The kernel has 7 million objects. Well, Chromium has more than 20 million. And when you put that all together in your pack file, so you end up with a repository of 23 gigabytes. So definitely, that's not a size of a file that you want to send through the wire, and even manipulating it in the server can be problematic. So, and what have we been doing in Git to kind of handle these numbers? The first obvious point or place to work was in the protocol, that is the conversation between the client and the server. So yeah, we were working in the protocol, especially trying to avoid this sending unnecessary information. And the other big point, I guess, that is allowing the client to be more precise on what it wants to try to minimize what comes back and forth. But I'm not going to elaborate more about this because later today we have a talk by Brandon explaining exactly this work. So the other thing that we did is, the other point that we saw problematic is how Git works is that the client talks to the server, they chit-chat a little bit, trying to figure out what is the minimal difference that they need to transfer that both can be on sync. So, and the conversation more or less goes like this. The client says hi, the server answers yes. Look, I have master pointing to this commit G, and maybe other references. The client says, oh, I don't know about that, so I want that commit G, and the last thing that I have is C. So figure out what is happening here. So the server now needs to calculate that difference with this information. The obvious way to implement this is you could think that you're starting your want commit, and you start traversing your tree until you hit something that the client has, and what is in the middle is what you need to send. And in this case, it would work really beautifully, because this is a very simple one. Once you start having branches, merge commits, and a more complicated topology, things are not that easy. And also, what happens is that to do that, you need to read the commit, parse it, extract the parent, check if it is in your hub. If not, repeat this process. So actually retrieving a lot of information. To solve all this, we came up with the idea of the reachability map, bitmap. The reachability bitmap is a small bit structure that is attached to the commit and tells you what other commits are reachable from it. So assuming a tree like you see on the left, so at the end, how Git stores the information is putting all the objects one after the other in what is called the pack file, and then it has a pack file index that says this commit is in this object ID is in this offset, this commit ID is in this offset, and so on. So you end up with a list of commits. And the bitmap for a commit pretty much has a 0 if it can reach that other commit, or a 1, a 0 if it cannot reach it, or a 1 if it can. So in this case, for example, from the node G, if you would walk backwards on the tree, you can reach every other node except D. So it has a 1 in every position except on D that it has a 0. If you check the other extreme, for example, in the case of A, it has a 0. You cannot reach anything from node A. So, and what's the point of this? Well, that now the client says, I want G, and I have C, so the server can retrieve those bitmaps, and the fact of calculating the difference is doing bitwise operations, and we don't really need to crawl through the information, which is much more effective. The next thing that we saw is that Git is designed for a distributed development environment where you have just developers with their local copy doing their work and sharing small changes. And the clone is pretty much a one-time operation, very expensive, but you just do it at the beginning and that's it. But what we are seeing is that there are other cases, and we start seeing cases like the containerized continuous integration, for example. This is a short-lived client. It just wants to come up, grab a copy of the code, probably of the last commit or maybe the last 2 commits to make some analysis and calculating diffs, and do their work and disappear. And definitely the default clone is terribly expensive for this case. So then we have the option of the shallow clone. Shallow clone is, I think that conceptually is very easy. So if you have a tree like this with the commits A, B, C, and D, each one has its tree. That inside can have another blobs and files, and maybe other nested trees, and all this structure spawning. So when the client says, I want just a shallow copy of this with a depth of 2, it will receive just the commit D, commit C, and everything hanging from there. Everything else in the repository will disappear. And in the graph is only few points, but this can be a long history with a lot of other objects and can save a lot of space in the transmission. The problem is that calculating that efficiently is not trivial. The optimizations that we talked before with the bitmap are for commits, not for the whole trees. So we still need to dig through the pack file to extract all those trees and objects that are needed. So far, we don't have a very good solution for that. Plus, think that if you have a pack file like Chromium of 20 gigabytes, well, good luck of trying to get pieces of that randomly. And still, shallow clone seems to be a good solution for this. Don't confuse it with another feature that is coming now in Git, that is the partial clone, because in the case of the partial clone, the client actually knows all the objects. In the case of the shallow, everything below that cut point is simply invisible. In the partial clone, you just know it. You're just saying to the server, don't send it to me now, I will tell you later. And yeah, these were mostly problems that are related with how Git is designed and work. Now I pass the token to Minh.
Well, thank you, Ivan. Good morning, Git Merge. I'm going to switch gear a little bit and move away from the theoretical implementation that Ivan has went through and share some example of the use cases that keep us as a Git hoster be on our toe. Let's see. Most version control system outside of Git have some notion of revision number that is increasing. It may be continuous or non-continuous, but it's always monotonic, and that's very useful because it kind of gives you a sense of directions of, okay, I'm going that direction. As a matter of fact, a lot of organizations will celebrate if their developer have checked in some milestone number of changes, like 1,000, 10,000, or million. So it's part of the culture of software development. And Git comes around and, let me see, Git use hash as a revision number, and hash is not increasing. And for a lot of organizations, that would be a blocker from deploying Git as a revision control system. So software developer, you come up with a solution. You work around it somehow. And the typical workaround is to implement revision number in the commit object, or more specifically, in the commit message. So here's an example that we have with Chromium. The Chromium project moved to Git in 2009, almost 10 years ago. And they migrated from SVN. And if you're familiar with SVN, have an increasing revision number that would send back to you after you do the commit. And a lot of the software has been built to rely on this property. And like I said before, the developers often refer to the revision number in communication between organizations, and that's nice. So when moving to Git to keep the existing workflow, they create a new developer workflow to make this work by have developer push all the code changes into a branch called the branch head master. And for every commit into this branch, they would have a bot that watches the branch and copy that commit over to the main master branch. And while doing so, it alters the commit message to attach a revision number. So this works, actually. It works for many years. But this has a side effect that as time goes by and the revision history gets deeper and deeper, the fetch time gets longer and longer. And it gets to the point where we as a host have to do something because it's not productive anymore to wait so long to fetch. And we went through the analysis, and well, what's happening here is we have the double number of commits to negotiate through. And negotiation, as mentioned by Ivan earlier, is a process in which the server and the client have to show what they have and what they want on all the branches, not just the one that you're interested in right now. And so now you have more commit to negotiate through, then you will have a problem. Another problem that was not transparent to the client was that in the Google implementation of the server, we do not have reachability bitmaps outside of ref heads and ref tags. So something in the ref's branch head master will require a full ref walk to check. And if you have a deep history, that can be very expensive. Now, you know, there's something that we can do from server side to include this in the reachability bitmap that make that happen. But the lesson that we learn from here is there a right way to go about this problem? And you know, I personally don't think that we should try to solve this problem and encourage people to go Git native and get used to Git hashes and you know, get used to Git log to see the revision history. And that's good anyway because it gives you way more information than a single digit would give you. As far as releases is concerned, you know, it still have value in having increasing release number, and you can use tag to denote these things, and you can use git describe to show the tag. The lessons from this experience is do not try to bake a number into the commit, because if it's subject to change, you're going to get into trouble, because when you rewrite history using rebase or something, things are going to get mismatched and potentially out of order really quickly. So, the question you may have is, what happened to the Chromium projects? So we did a certain amount of server-side adjustment to make it work faster, but at the end of the day, they got rid of the bot because having the double number commit is just not feasible. And they switched over to a different source review system that allowed them to amend the commit message when it's being merged in. So they still have the increasing revision number, but avoiding the double commit problem that we had before. Yes, it's go against our recommendation earlier, but they want what they want, so they got what they want. Okay. So the second story is a lot more recent, and it's not necessarily about something that the client do that against our recommendation, so which is ironic. Gerrit is a code review system that built natively on top of JGit, which is a Java implementation of the Git protocol. And here in the graph is a typical commit tree of a Gerrit project. So you got two changes going on, change one on the left and change two on the right. Change one on the left have two different path set, and change two on the right have three path set. So you got a bunch of refs pointing to a bunch of branches everywhere. And Git server loves this because you got a big tree, we can build a bitmap, no problems. But recent development in the Gerrit system is that instead of storing the metadata that related to change review comments and ratings and all the thumbs up, thumbs down in the SQL database. We decided to store that inside Git itself. So now, Git not only stores source code, it's behave as like a data store, like a generic data store, which is quite novel because you have one single Git repository that contains all the history of the code change and the review that makes this code change approved, which is very nice. But the problem is the change meta is stored in a separate tree than the code tree. And there's no relation whatsoever between the node, which is denoted in red in this graph. And anytime for every single pass set, there's a new branch that created for that. So you end up having a lot and lots of little commits to sort through whenever you do negotiations. And as I mentioned before, a lot of commit is best for negotiations. And this is becoming a real problem as time go by, and you have thousands of active changes happening, so that the change that you have is actually more recent than the change in the master branch. So negotiation would give up because it doesn't want to take so long before it finishes. And what happens when the negotiation gives up is that the server will say, OK, I don't know what you want, so I'm going to give you the whole thing. So a single change, when you do a fetch, may result in a, 10 gig clones that would take forever and are very costly for both sides. So how did we solve this problem? There's protocol v2, which is the biggest savior for us, which refs in one. We can, the client can specify the list of refs that it wants. So the server can say, oh, if we're going to just interested in this ref, we're just going to negotiate within the commit from this refs. And that go from these hundreds of thousands of refs into just a couple. And that helps a lot. Another change that was done in the protocol is the ability to make this negotiation round bigger. So instead of sending 32 SHA-1 in one round, you send 256 or something, because each of the negotiation round can take time for round trip. And another change that is we go longer. So you trade the time of negotiation for the time of downloading. Another change in the protocol that was very useful was instead of walking back in the commit graph one by one, it can actually skip in some fashion. One of the ways to do it is a Fibonacci number, so it's increasing in gaps. And the idea is that we sacrifice the ability to minimize the pack by getting to a common commit faster. And all this, if your tree is deep enough, it's OK to send a few extra bytes. So, as a host of a Git service, we have a wide variety of use cases, and things evolve all the time, and we always have lessons to learn. And if you want more details about any of the things that we presented today, you can find us later. And thank you.
Yep. Thanks.